All right, let's get started. Yeah, welcome everyone. Today is Fault Tolerance Day, and we're starting strong with our very own Chris Pattison, who will tell us about how to do fault tolerant computation with a constant number of control lines. Please take it away.
Great, thanks. So this is joint work with Jungwon and John. I'm going to tell you about some kind of potential direction to build fault-tolerant quantum computers at a very, very large scale. And it's something that's like kind of, I'll disclaimer, it's something that's like kind of very futuristic because there's a lot of things that have to go right in terms of hardware advances in order to actually make this happen. Some parts are maybe kind of really in the weeds in terms of our construction. So I've put a little emoji in the top right corner whenever you can, take a little nap at the request of an audience member. OK, so currently, the way that people intend to build quantum computers might look something like this. So let's consider a 2D solid-state platform. So say a superconducting qubit system or a spin qubit system, something like this. And you have kind of some grid of qubits, and then you have these kind of connectors that connect to the outside world. And then you have to route kind of control lines into this bulk of qubits. And currently, the way people are thinking to build these devices, we have universal control over each of these qubits. And in particular, we have a constant number of control lines per qubit. And so if we have, say, 1 million of these things, then we need kind of 1 million connectors and kind of 1 million wires going into this qubit kind of lattice, which might be at like a much smaller scale. And so there's kind of some area perimeter issue. And this is kind of pretty extreme in some cases, where for some qubit technologies, your qubit might be as small as, say, 10 nanometers or a few dozen nanometers. And then in other technologies, OK, it's less of a problem. Your qubits might be hundreds of microns. But your connector itself, at least with kind of a standard like coax connector, the scale is like millimeters, right? So in some sense, these pads are going to be very, very big, whereas these qubits and the spacing of this lattice is going to be quite small. And so if I have one pad per qubit, that starts to become a problem. So classical processors scale really, really well. A current state-of-the-art, a typical state-of-the-art processor might have on the order of 100 billion transistors, where a transistor kind of being your atomic unit of kind of computation, you should think of as kind of a qubit. And we don't universally control all our bits in our classical processor, right? And the general idea is that the majority of what the circuit is doing is fixed at manufacturing time. So here I have a picture of a processor manufactured in the 1980s. It's a very famous design, the 8086. And this has roughly 30,000 transistors. And you can see, if you look really closely at it, those connectors that I showed you previously are kind of these little pads at the periphery of the chip. There's only about 40 of them or something like this. So kind of we have tens of thousands of transistors in the bulk and a very, very small number of bits of actual control going into this device. And this sort of, this ratio is even more extreme in a modern processor where we have 100 billion plus transistors and maybe only a few thousand pins. So the thing that allows this to be like kind of possible is that you have these fixed function components, and they're wired to their neighbors. Like your data. So typically, whenever we have universal control of our qubits, we're applying our qubits, our actual quantum data is kind of fixed at some spatial location, and then we're just applying operations to it. Classically, you stream the data through your operations. So it might look something like this. In particular, so we might have some configuration of gates, which is kind of what everybody is kind of already familiar with. And in addition, we have these extra circuit components. And what these extra circuit components are, so the digital logic people call these registers. And what these registers do is they receive this global signal called a clock. And the clock just kind of oscillates between 1 and 0. It goes high, low, and so on. So if I imagine that we have inputs to this clock, what happens is at the rising edge of this clock signal, all this register does is it takes the input and just copies it to the output. Something like that. OK, great. And now these gates, these are just some configuration of transistors. Once you've held the input to the circuit to some value, kind of what will happen is the circuit will settle to some computed value. And it does so before the next rising edge of the clock. And then you have the next clock cycle. The input gets copied to the output, compute a little bit more, and you have your answer. And then eventually it appears. So this is just an adder. But roughly, we would like to copy this quantumly in some way. And then we can kind of hope that, all right, well, maybe we have some analog of a clock signal, which we will have. And then maybe the majority of the wiring that actually does the computation is all local. OK. So we can copy this, except we can't copy. So we want this ability to just transport quantum information, and we want to kind of be able to hardwire components of our circuit. So kind of one observation is that suppose I have a circuit that is in one dimension. It might have, so I lay out my qubits in space, and then I have a time axis. So it looks like something like that. And what I can do is I can start to lay out, for every space-time location of this circuit, I can lay out a location in space, and then kind of execute the circuit with some period 3 thing. So in the first circuit, or sorry, in the first layer of this circuit, I'm going to apply some layer of gates corresponding to my layer of circuits in the original circuit. And then I'm going to perform 2 layers of swap to move this forward, and so on. So kind of a qubit that starts somewhere like here, gets one gate layer applied, gets shifted forward, gets another gate layer applied, shifted forward, and so on. So this is starting to look a lot like what we had previously. And you can kind of do this kind of to some very large extent. And kind of importantly is that this preserves the structure of the faults. If I have, so this thing right here is some periodic thing. And if I have a fault at a particular gate, at a particular location, that corresponds to a gate being faulty in this circuit here, which if I've constructed this to be from a fault tolerance scheme, then I might be good to go. Yep.
Does this thing have to be periodic? Actually, each one of these gates can be different?
So this is not periodic, whereas this is. So kind of I've taken something that is not periodic, and I've kind of unrolled it into an extra dimension, an extra spatial dimension. And this thing itself, it doesn't have to be periodic, but I'm going to want it to be periodic because I'm going to hard code a lot of things.
Sorry, I'm a little confused. Are you saying that you want to do gates at fixed locations in the chip?
Yeah.
And where is that on this periodic thing?
So I'm going to put a qubit for each of these circles.
Uh-huh.
And then for every location, this is going to correspond to a location in this circuit. And I'm just going to be performing this gate and then 2 layers of swaps. So you have some data that initially starts right here. If I want to perform this circuit, I just apply, in this case, 8 rounds in my period 3 circuit, and it just kind of propagates. And at the end of those 8 rounds, my data is here, and you have, and it's had this layer of gates applied to it.
And here, the number of gate locations is still a lot, right? Every layer of the space roughly have 8 locations.
It's a lot.
Okay.
It's a lot. Yeah.
Sorry, this is something so why isn't this just a 2D circuit to begin with?
Why wasn't it a 2D circuit to begin with?
I mean, isn't a 2D circuit just laid out in time so that you're...
Well, I've laid it out. I'm laying it out in space now. Yeah. So the point, I desire something that's periodic for reasons that will become clear momentarily. And then I need to kind of construct something that does something non-trivial.
Sorry, but so maybe there's something I'm not understanding. So I mean, there are 2D circuits which are periodic to begin with. So why would we have to be a periodic? So what is it about the 1D circuit and what does it mean a 1D circuit and in the first place? Can you say what?
Yeah, so in particular I want so a 1D so a geometrically local quantum circuit. So kind of there's a sense in which I have kind of a spatial direction and I can just kind of put it out and then I'm just applying gates.
How do you think of it working? So does it compute from left to right or what's
the 1D circuit?
The 1D circuit, yeah.
So essentially what I'm going to do in 2 slides is I'm going to take a 1D quantum fault tolerance scheme and I'm going to put it right there and I'm going to map it to a tile. So my 1D fault tolerance scheme has these gadgets and you
Yeah, no, but I'm still not, there's something I'm not following, which is what's the role of the 1D there?
Sorry?
What's the role of 1D there? Usually when you have a 2D circuit, I see, okay, it's 1D. All right.
Okay, great.
Maybe just to clarify, when you say periodic, do you mean periodic in space or in time?
In time. Yeah. So this is a depth 3 circuit that I've constructed from this 1D circuit that was not periodic. And my main goal was to make it periodic. And the reason I want to make it periodic is if you zoom in on what this kind of looks like, suppose that all my qubits,
Or what do you mean by depth 3?
the-
Or I mean, it wasn't obvious to me that what was happening on the right-hand side was depth 3.
or period 3.
Or,
Yeah. So I can implement this circuit.
and that's
With-
not periodic. That's just
That's not periodic.
those are arbitrary.
Yeah, that's not periodic. Is it clear that there's a period 3 circuit here that implements this circuit?
I don't really see where the periodicity is, other than the fact that there are shapes.
So in layer 0 of my period 3 circuit, I'm going to apply this gate at this location, this gate at this location, this gate at this location.
Oh, you mean
Layer
period 3
0.
in time?
Yeah.
Oh, okay. Yeah.
So my data is going to be propagating forward.
Yeah, no, I thought you
with
meant
each
period
cycle.
spatial. Yeah.
Yeah. Okay. Great. Okay, so the reason I wanted to do this is suppose that your qubits are identical, that's a big ask, and I'll get to that at the end. And then suppose that your gate set's finite. Then you can start to think about kind of having something along the lines of classically when we had a clock. So I've here drawn maybe I have 2 gates, magenta and green. And then I can start to think about sharing the control lines. I, for example, have in my kind of 1 layer of my period 3 circuit, it's a depth 3 circuit, for every type of gate in every layer, I would have 1 type of control line. So if this is gate A, I just have my A control line, and I have my B control line. And the point is this constant number of gate layers, constant number of gate types, that's a constant number of control lines for these global gates. And I'll get to another notion of control line in a minute.
Can you say a bit more about what you mean by it?
So suppose that if your qubits, suppose I want to do a Hadamard at these locations in step 0 of the circuit, right? If your qubits were identical, you could imagine sending in the Hadamard tone such that you do the Hadamard.
Oh, it's like the same pulse.
Yeah,
Okay.
that's right, yeah. Okay, great. Yep.
Can you, so when you say finite gate set, you're saying that you only have a constant number of control lines. So you have the green control line, the purple control line. And when you say finite gate set, there's only a certain number of gates that you're able to apply. How does this translate to having universal control in your device? Because it seems like you have to fix what P has to be at the time of manufacturing. How do you get universality?
Yeah, so I will discuss that over the next 30 minutes. Okay, great. So already this is enough to build a memory. So first off, there exists one-dimensional fault-tolerant schemes that are measurement-free. So I can just, there's gadgets you can write down. They're geometrical local in one dimension, and that gives you fault tolerance. And so in fact, you can do this without measurements. There's also versions that you can imagine with kind of local, like classical control, something like this. And roughly the idea is that you take a one-dimensional concatenated, or you take a concatenated code scheme and just do a bunch of swapping. It's like one way to achieve it. Great. And then you're going to take the identity gadget of this fault-tolerant scheme that just implements error correction, and you're just going to kind of apply that transformation that I showed previously, and then just arrange them end-to-end in a ribbon. And what you have is you have your data kind of circulating around in this ribbon, and you have your code blocks kind of as they're circulate around the ribbon by applying this repeated applications of the step 3 circuit, they get error corrected. So far, so good. Great.
I guess when you say error corrected, do you mean like measure stabilizers and decode?
So in particular, I'm applying this. Yeah. So there is something that morally looks like that, but it's all happening locally. That's right. OK, good. So I gave you a ribbon. Ribbons are not really things that we manufacture. I actually want a 2D construction that genuinely uses a lot of the area of 2D. And in particular, I want it to be on a square. And the reason being is that kind of the difficulty of manufacturing a device in classical logic, or classical like semiconductors, is kind of proportional to the largest length scale in the device. So naturally, you make chips that are squares. So how do you do it? Well, you just kind of fold it over. So I took that ribbon, and you fold it in half. And I'll tell you how you actually implement that kind of microscopically. And then you just have kind of your code blocks kind of propagating around the ribbon. And kind of as they fall over your crease, they start propagating kind of in another direction. And during this kind of operation, all your qubits of your code block are kind of within a constant. You can still kind of achieve the constant connectivity even as you're kind of turning. OK, great. Now, the way you actually do this is kind of some complicated network of swapping in terms of and flow of the qubits. But you kind of just, it can be done. It's not too bad. And what's going to follow, I'm going to write these kind of magenta, or these pink ribbons a lot. And kind of the picture you should have in your head is kind of some configuration like this that came from these Aharonov and Benor gadgets.
Where did 2D come in the sense of like, why couldn't you take your 1D ring and then just have it be like 2 lines or something?
Say one more time.
Like, where did the 2D come from? Like, why couldn't you just take your 1D ring and just make it like 2 lines that were like a circle? Like you had a 1D ring.
Well, it's kind of had finite thickness, but yeah.
I guess, or does that count as 2D?
I mean, like it counts as 2D, but I'd like to have something I can manufacture that kind of uses up as much area efficiently as possible. And for that, I want to be genuinely in a square, actually. I want kind of, the thing that I should care about is not actually how many qubits I have, but like roughly what's the spatial extent, what's the largest kind of dimension of the device. Okay, so kind of, if you look at this like a path of a qubit, you might start here, you kind of go, fall over the corner, and then you keep propagating upward. So kind of microscopically, it's not too involved. Okay. OK, so now we can have some 2D memory that is arranged roughly in a square. So just to have some result, roughly you store logical qubits with some polylogarithmic size overhead. It's a memory. And this is kind of everything you would expect. And then something that you get kind of for free, which is that the circuit is actually naturally tolerant to fabrication errors. If I have some dead qubit that's right here, as the code block propagates past, I have some location in the implemented gadget that's faulty, but that's fine. It's just that every time that gadget gets executed, I have an error in that space-time location. But from the point of view of the propagating data and the gadget that was implemented, that's still a local error. So great. Now I'm going to build a computer. And I now have to specify a little bit more about what my model of computation ought to be. So first off, I want to take some quantum circuit that my user would like to sample the output of. And you're going to compile this, and you're going to write it to an input tape. And then you have this hard-coded quantum circuit, or almost hard-coded quantum circuit, that is going to be kind of in the device. And OK, you have kind of these shared global control lines that kind of go everywhere across your chip, and that's fixed at manufacturing time. Then you have a small number of qubits that I call control qubits. Those I actually do have universal control on. So when I run my device, what I'm going to do is I'm going to be blasting this hard-coded circuit. And the actual controlled qubits, I'm going to be just writing to them the kind of whatever I wrote on the input tape. And then I'm also going to be measuring some of them, too. And I'm going to write that to some output tape. And then I'm going to post-process that. And that's going to be just the full procedure for running this device. OK, great. So in terms of how their classical processors are universal with a very small number of controlled bits, have this picture in your head where you have something hard-coded. And then each time you have, nobody can see this, but there's a wire kind of coming off of the screen here, and some pad right here that's kind of somehow going into the bulk. Oops. So the major idea that allows this to work, classical processors, we call them circuits, but they're not kind of in the circuit model of that computer scientists think about. They kind of more look like a Turing machine of some finite size. And the general idea is that we're going to reuse circuit components. So ignore this control line for a second. We can have some classical data that just keeps running in a circle. And so kind of whenever I write something here that's ostensibly a circuit, it's kind of, you should think of it more of as a fixed configuration of hardware that implements some circuit if you kind of move data through it. Now, in terms of actually being able to program this thing now, suppose that I had my one controlled qubit or something like this, and that these are maybe some really, really complicated operations. And I want to do some sequence of them, operation A and operation B or whatever. Well, I just take my control, and I route the data to either operation A or operation B. And by choosing which direction the data flows, I can implement some pretty complicated circuitry using only a small bit of control. Great. And we're going to do something like that quantumly. Suppose that I had on these these propagating code blocks some sequence of ones and zeros that I'm going to call control bits. And these are encoded in some quantum code. I'll tell you where they come from later, but because they're encoded, this is kind of noiseless. And also note that my 1D fault tolerance scheme gives me kind of a tile that is a configuration of hard-coded gates for each operation. So state preparation, Hadamard, control swap, Toffoli, any of the usual things that you want, I can hard code a logical gadget in some particular location. So I can do something like this. So imagine you have here that's circulating memory tape from my memory. And then if some logical qubit comes by that I would like to do, for example, a Hadamard on, I write a 1 to this control stream, swap my qubit over to the Hadamard, and then swap it back onto the tape. So some sequence of 1 and 0s is going to determine some sequence of Hadamards that I apply to the tape. Great. So now it's starting to look a lot like the classical machine. This is a technical ingredient, which is that on this memory tape, I need to entangle code blocks that are at different positions on the memory tape. And to do it, you have to kind of make one propagate faster, kind of some code block propagate faster than another code block. And to do it, we're just going to kind of skip over some position on this in this hard-coded circuit. It looks something like this. So I just kind of swap a little bit faster. And OK, you incur some overhead of like you needed to build a slightly faster swap, but this is fine. Everything's still constant. Cool. So given that, we can start to augment this tape with universal operations if I have this stream of noiseless control bits. So my operation is going to be I measure a qubit of the memory tape, and I set it to 1, a Hadamard, and then this kind of annoying thing, which I promise applies controlled S to 2 consecutive qubits of my tape. So kind of as my tape is circulating along, I'm implementing some one-dimensional circuit with this gate set. And what I mean by measurement here, I'll get to at some point. It'll be essentially the opposite of the way I get the control qubits, the way that my computer talks to the outside world. So now, the actual control bits themselves, I have to tell you where those come from. So first off is that these controlled qubits, I can control a single position on my device, right? And in particular, the only thing I'm going to do is I'm going to set it to 1 and 0, and I'm going to measure it and write it to the output tape. And then I can kind of encode this thing into the concatenated code, like a Aharonov and Ben-Or. And I can do this with an error rate that depends on my gate error rate. So kind of the picture you should think about is in terms of these kind of ribbons. So I had 1 qubit, and it kind of got bigger to the full ribbon, and I have some noisy state. Cool. So now I can compute on this thing. And to get noiseless control, I'm going to do something very simple, which is I'm going to use a classical code. So your controller sends some sequence of noisy bits that are code words of a classical code. It might look something like this, although these aren't actually noisy. I forgot to add the noise. And you have kind of that these are represented in kind of code blocks. And OK, so you do this encoding step to the concatenated code. And then I'm just going to run the decoder of my classical code on this time sequence. So it might look like that. And this decoder itself, I'm going to take these Aharonov and Ben-Or gadgets, and for every gate of that decoder, I'm going to place down a tile that implements that gate, such that as the data gets streamed through, it implements the decoder. Great. And now, I mean, like this is a very technical detail in terms of how this actual decoder actually gets implemented. There's this trouble that kind of I need a notion of I need to know whenever I have an aligned frame. So what I'm going to do is I'm going to look at a window of this data stream. And I'm going to look at this window by kind of copying out this data stream many times and kind of implementing some delays. And then I'm going to have this periodic signal that's going to be 1 every so often to kind of mark off where the frame kind of ends, the boundaries. And this I'm also going to get from some primitive like this, and then I'm going to take some majority to get rid of the noise. Then I'm going to run my decoder. It's looking at a bunch of consecutive bits of this stream, and it's going to decode. And in particular, it's only going to output something non-trivial if I see a 1 on this kind of metronome. And then I'm just going to add it back together such that I get kind of a decoded data stream. Yeah, so these ones. Every time you see a 1, you know that you're looking at a position like here, for example. Great. And that's where my noiseless control comes from. And you can do some similar procedure kind of in reverse for the measurements. OK, so now I'm ready to give you a processor. So, OK, so remember that classically, we fabricate some computer chip, and it runs any circuit of some fixed size. You know, I have some memory. That's like kind of the maximum amount that I'd like to run. And also my chip has like some error rate. You know, it can't keep running forever. So there's a maximum size of computation that I can run. And that's fixed at the time that I actually fabricate the chip. And we have the same thing. So we have a memory. I've abbreviated that. We have some constant number of control qubits. The device can kind of initialize itself. You don't have to control the initial state. And then we can execute some arbitrary quantum circuit with kind of, at most, this number of qubits. In time, that's kind of proportional to the circuit size times the space. There should be a polylog right there. But it's something like this, right? So kind of, this is pretty slow. And I'll get to that in a minute. But and then we also have our threshold statement, sort of that if your error rate is below some critical value and your circuit's not too large, then you get correct output, even in the presence of some amount of local stochastic noise. Great. Yes?
Conceptually, when I think about the time overhead, should I think of it that you have a one-dimension, essentially your qubit is like a one-dimensional unit, and the number of gates times W is just the cost of going one cycle of this ribbon.
Yeah.
And in this one cycle implemented, that's layer of gate.
Yeah, that's right. Yeah, exactly this. Great.
And when you say constant number of control qubits, I should think of there being a constant number of like these gate locations that's attached to this ribbon, or is it like multiple gate locations, but many of them are like the same Hadamard, so.
The latter, yes. So so you have kind of these global signals, right, which is analogous to a clock signal in the classical processor, right? And then and you only need a constant number of those global signals, and that's what's doing kind of the bulk of the computation. Kind of that's what's causing everything to propagate, and while it's propagating, it's getting error corrected. And then we have this constant number of controlled qubits, where I individually am like kind of able to control it. And that's kind of where I'm directing the processor what to do. But it's a very kind of indirect thing, right? The actual way in which it, like ultimately the processor does the thing is kind of separated by many different data processing steps to get to that point, much like a classical processor.
And I should think of the control qubits as receiving a stream of control classical bits that
That's
I
right.
need to execute.
Yeah, yeah. And in fact, we're just using this in a classical manner. Yeah.
But just to clarify, like when you say C not too large, is like the dependence different from like the usual photonic sphere?
I actually have 2 parameters, which makes it really annoying. And you fabricate this thing ahead of time, right? So you fabricate saying, this is the maximum space that I'd like, and this is the maximum depth that I like. And then, yeah, it's really troublesome. Yeah.
Just to set a classical sort of baseline. So in a classical computer, does each control line address only a single location, or can it address multiple locations?
So your control line, kind of that pad that I showed earlier, that's going to the gate of a single transistor. And that transistor is maybe driving more transistors. And that's going to go kind of onward to do something very, very complicated. So in one sense, yeah, it's controlling a single thing. But kind of indirectly, you're kind of doing some very complicated operation. So it's essentially identical to what we have here,
But I thought
up to the time overhead.
But I thought here we had maybe one control line for Hadamard, and it's hitting multiple locations.
Yeah, so the analogy of the control line for like the Hadamard or something like that, these are not Hadamards that you want to implement at a logical level. These would be kind of your kind of this background like period 3 circuit that's being implemented, it's implementing that. And the analogy of like a clock signal or something like that is every time, so classically your data propagated according to this clock, right? And one cycle of that clock is analogous to one cycle of this period 3 circuit, and both are implemented by some global driving. Or when I say global, I should be a little bit careful. It's some hard-coded, very specific driving. But generally, it's with a constant number of control lines. Classically, it's 1. Here, it's probably more like 10 or 20, but it's a few.
What's the size of the number of bits in the input tape?
It's this length here. Yeah, it's for every time step of the period 3 circuit, I go to a new position of the input tape.
Yeah, so just to clarify, so you said that this W is the time of like one cycle of the data passing through this ribbon.
Yeah.
Why does this grow linearly in the number of qubits? Like, can't you just make the ribbon wider, or does it somehow inherently make cycle time also longer somehow?
You can make the ribbon wider. That's fine. In fact,
like, I guess I'm wondering, why does it scale linearly in the number of qubits? Like,
I mean, like there's, I'm going to do a lot better in a minute. Yeah, okay, let's get to that. Okay, great. So we want to go faster. It's pretty slow. And the main bottleneck is that I have this one-dimensional ribbon that's like kind of circulating, and I have to do this one at a time. Kind of, if I need to bring my operands together of like some operation, kind of, already I kind of have this like square root of the circuit size kind of thing. At least it would appear without some funny compilation things. But you can imagine something else. And what I'm going to do is I'm going to extend my model of computation a little bit. I'm going to give myself classical wires. And what I mean by classical wire is I have some units that you should think of as kind of on the chip somewhere. And they're connected by a wire. And whenever this unit here drives a 1 or a 0, that 1 or 0 is propagated to all the other units simultaneously. And I'm still requiring that these wires are kind of fixed at manufacturing time, and I have unit density. So in some sense, this is just like a wire in a classical processor. Okay, even there, the signals don't propagate truly instantaneously, but this is kind of what I think to be a reasonable model, and I'm happy to chat about that more. And then, okay, so using that, you can have instantaneous quantum signal propagation. Kind of the idea being is you just pre-share your entanglement, and then you just run some teleportation protocol. Cool. So now we have, now if our operands are far apart, we could hope to teleport them close together. And that's what we're going to do. So we're going to build a random access memory. And by random access, I mean in the more traditional sense. I don't mean at QRAM, where I have classical addresses, and I want to get some qubit here, some qubit here, and I want to pull them out. And the way I'm going to do it is, instead of that one really big memory tape that was circulating, I'm just going to have many small ones. And then I'm going to teleport along the length of this memory via some entanglement swapping circuit and then some like global parity calculation. So, and then you just take this thing and you just bolt it onto the previous construction. So what this looks like, and it's a bunch of details, is essentially for each of these kind of cells, you have, you're exchanging bell pairs with your neighbors, you have some small storage tape, and then you have some circuitry that decides, okay, should I teleport something off of the storage tape, or should I participate in an entanglement swapping protocol with my neighbors? And I can decide this all locally, and then I have to send out the parities via my, my wires to actually complete the teleportation protocol. Okay, great. So now we have essentially the same statement, except now in this model, that time overhead got dropped dramatically. So now we're at polylog. So we're in pretty good shape. Okay. And in fact, this essentially to the extent that you can even assign an asymptotic scaling to a classical processor, this kind of matches it. Kind of in some sense, if I'm executing gates at one at a time, I have to, if I have a constant number of control lines, I can only specify a constant number of gates per cycle. And in fact, I need logarithmic bits to do that. So I can only do kind of a gate at a pace at which I can describe the circuit to compute. So this matches. Great. So then you might ask, well, hey, that was a pretty slow time complexity, or like runtime. Why aren't quantum or classical computers so slow? I mean, like mostly we think of them as being pretty fast, right? And the main reason is that there's a very large computer architecture bag of tricks that we use to kind of hide this asymptotic like poor performance. Whenever we implement an instruction in a classical processor, we're not really kind of implementing gate by gate, right? We might do something quite complicated that actually matches the workload that we actually want to run. So for example, we might say, multiply these 64-bit integers, right? And that's kind of launching off some computation that's using a ton of gates. So you really want to find instructions that kind of match the computations you would like to run. There's also this idea of pipelining, which is before the previous instruction finishes executing, you kind of are executing the next instruction. Actually, we were secretly using that idea previously. And then you can also have multiple cores, right? So a modern classical processor might have a CPU, can have anywhere from like 10 to potentially a few hundred cores, right? And those cores are working on independent pieces of your classical circuit that you're actually executing. And you can imagine something similar here. There's also this question of whether or not you can manufacture this thing. So there was a part earlier on where I said, assume that your qubits are identical such that you can share control lines. This is actually kind of a big ask, right? We would either need to reduce the manufacturing variance in some way, right? That we have some tolerance, fortunately, because we have a fault tolerance scheme, but we would need to kind of either be able to fabricate a qubit that requires very minimal tune-up, or be able to do some serialized tune-up in a way that doesn't require a control line per qubit. Or maybe we can do all this tune-up and control generation kind of locally. Fortunately, it's naturally resilient to these manufacturing defects. And there's also a lot of threshold tricks that we can play here, right? So here, I used an all quantum scheme for the fault tolerance, but really, in some platforms, you can imagine kind of having classical logic kind of running right next to your qubits, as long as you satisfy kind of unit density and things like this. So there's a lot of optimizations that you could hope for. And then, yeah, just as a reminder, this is not really near term. And this hardware, in order to gain the advantages of having kind of a few number of control lines and scale to a really large size, your hardware should look kind of fundamentally very, very different from the way that we build it today. And stay tuned for some upcoming work by Nathaniel and others. And with that, thanks.
Okay, thanks, Chris. We have plenty of time for questions.
Maybe just a naive question. You have fabrication defects, and they're below your threshold. Like, I don't know, let's say half of them are below your threshold, or it's like half the threshold error rate. Then is it as simple as just saying that half my errors are permanently coming from these things, and then the other half are from actual errors?
Almost. There are some locations of which there's only a constant number that a manufacturing error there just kills the chip, which actually is what happens classically. Well, okay, classically you're not really fault tolerant to begin with, except with a few examples. But if your wires that you're using to communicate with the outside world, if that's dead, then you're host. Fortunately, you only have to manufacture the chip once, and maybe, okay, 1/3 of my chips are dead, but that's not a problem. And then the rest is just you have a permanently dead qubit that corresponds to an error always occurring, but that's fine. You're fault tolerant.
Sorry, I'm still struggling a little bit with the definition of control line.
Mhm.
So is it fair to say that any non-adaptive circuit, 1D or 2D, or even any circuit that has a fixed period in time, is considered to be controlled with a constant number of control lines?
If that period is constant size, then yes, that's right.
So, for example, like even the central instruction for surface code, which is PRD4, can be considered as like with constant control line.
You have to read the measurement outcome, and that requires a control line to every qubit, every measurement location.
Oh, I see. So the problem is more like the classical
Yeah.
process.
That's right.
So is that, can you just, wait, so is there a bit of this trade-off in how much you use computer lines to extract, an architecture where you extract symbols and do your decoding classically versus doing the decoding
Can you interpolate between these two regimes?
Yeah, so
Yeah.
this one is, so are you on one side of this trade-off and you have to interpolating?
So I haven't described what an interpolation might look like, but you absolutely can interpolate. For example, you can use kind of these tricks to do the basic level of error correction, and then kind of at the higher levels, okay, now your processor is itself noisy, and then you're doing some interactive thing to do the decoding there. Yeah, you can absolutely interpolate.
Can you help me understand what would happen in a circuit with feed-forward? Like, what I can imagine is either you have this output tape, and suppose you want to do gates depending on that output tape. Do you have an extra processor there, or could you possibly think about doing some local processing depending on the measurement outcomes on your control qubits, and then doing some, yeah.
Yeah, so for simplicity, I described kind of a non-interactive setting, but you just as well could have an interactive controller, right? A controller that's like, doing some processing as well, and then it looks kind of not so different, right? As the out tape comes by, you kind of read what's there, you process it, and then you kind of rewrite the input tape. No problem. There is some latency whenever you do this because it takes time to encode and decode, and kind of there's this, but yeah, you can do it.
Okay, any more questions?
I have one more question. So in the scenario where you're doing this speed up from W to polylog W,
Yeah.
I'm trying to get like kind of the intuitive idea of what trick makes it work, and can I think of it as now that you have this broadcasting and you're also using quantum teleportation, you can kind of bypass the line with some of the routing of this qubits to execute the gates faster?
Yeah, I need to construct a memory where I can kind of retrieve very quickly kind of operands from kind of arbitrary locations in my memory quickly. Yeah, and I'm teleporting to do so. Yeah, that's right.
Can I ask, in the extreme limit where you have no errors and you don't have to encode anything, how does this thing look, if that question even makes any sense? Like what simplifies, I guess?
Well, I guess those ribbons now become one-dimensional, and everywhere where I use a gadget from, like, for example, Heronov and Benor, I don't need to do that. But so that's one way that you could envision looking like. I had some family parameter, you can just set that to 1. Where's it?
I have some sort of wild idea, so maybe you can comment if you think this was feasible. So in like these neutral atoms architectures, they have this idea that they continuously feed in like new atoms into the setup. Could you use this to make sort of like a continuous ribbon, like that you sort of stay in place and like
Yeah.
move it all the time?
So your hardware should look fundamentally different from the way you build it today. In some sense, with neutral atoms, you have this field of view, which you're kind of shooting your lasers through. And kind of the problem with atom loss and reloading is, at the moment, I'm not aware of a technique to kind of do this atom reloading and atom reloading, which you must do because you have atom loss. I'm not aware of a technique to do this in a way that doesn't require kind of doing atom rearrangement. Kind of, you would like that you have some, you kind of turn on some lasers for a while in some like, not even really in a field of view, just like you have some funny fixed optics, and it just kind of reloads itself, right? That'd be really cool if that can be done. Somebody should work on that. But at least for the moment, this is at least like one concern that I have about whether or not this will help us for something like an atom array. I will note, I need a lot of qubits, so laser power starts to become a concern. In terms of the size of the microscope objective, that becomes a concern. You can kind of get away with like, some issues kind of go away because instead of having stuff that's like programmable, you just have like kind of fixed optical like patterns, essentially. That gets easier, but then you need a lot of power. You're going to be a little bit slow, things like that. So I think kind of the ideal sort of kind of platform where this might make sense is something like some miniaturized superconducting qubit scheme, or something like a semiconductor spin qubit platform. Because there I can literally just put a transistor down and that's fine. And my qubits are fast and very small. And as a matter of fact, they're on the size of the control lines already. And so I have a problem with density. I can't really route them out if I have a lot of dots.
Okay, maybe one more last question. If there's any. Okay, if not, let's thank Chris again. And we have a short break, and then we meet again at 11.